Okay, so we have been talking about measurement of surface tension. So we discussed that surface tension can be measured by using two category of methods, force methods and drop shape methods. And in terms of force methods, we have discussed about the drop weight method. Now we will continue our discussion on the ring method. Okay, so typically in ring method, what is done? Circular ring is considered, and that circular ring is actually placed on the interface between the two fluids for which we have to measure the surface tension. So here you can see this is fluid 1, this is fluid 2. So typically in the initial configuration, interface will be flat, and on that flat interface we have actually placed the circular ring, and from the cross sectional plane from front side this will be looking something like this. Now we can define over here two radius. One is small r. So small r is basically radius of ring cross section. Okay, so when you have a ring, two types of radius can be defined. One will be the radius of the ring, and other will be at any section this ring is having circular cross section. Okay, so the cross section will also be having certain radius that is defined by small r, and capital R is actually the mean radius of the ring. So if you see, ring will be having two possibilities. One possibility is one radius you can define up to this point, and other radius you can define up to this point. In the scenarios where RR is very less in comparison to capital RR, instead of using two separate radius for calculating the surface tension force, we can define mean radius as capital RR. Okay, is this point clear? So this will be possible when the radius of the ring is very small in comparison to the radius of ring cross section is very small in comparison to radius of the ring. So once you have placed this ring, now because the name of the method is force method, so ultimately what we need to do, whenever we place the ring, we need to pull this ring in upward direction. Okay, once we are pulling the ring in upward direction, because of the adhesion, what will be happening, the bottom fluid 1 will be getting attached to the ring, and once this ring is moving in upward direction, this liquid is actually also getting pulled. So ultimately, in order to pull the ring, what you need to overcome, we need to overcome the, here one interface boundary is there, this is another interface boundary. So across these two sides, surface tension force will be acting at the circumference of the ring. Okay, so here you can see the downward force will be weight of the ring WR plus force because of surface tension, and we know that surface tension force is sigma into pi RR 2 pi RR. Okay, so sigma LF, which is the surface tension coefficient, and 2 pi RR is at one interface, inner interface. Outer interface is also is in contact. So for outer interface, again I will be having sigma into 2 pi RR. So ultimately sum of these two will become 4 pi RR into sigma. Okay, and one assumption we have done over here, I have already explained to you that for inner as well as outer sides, we are considering a same radius value which we are defining as the mean radius of the ring. Okay, and along with that, because we discussed about some correction factor depending upon the adhesion characteristics of the surfaces in the previous method. So here also we are having some correction factor Fr over here. Okay, and ultimately this is the net downward force. So in order to move the ring in upward direction, we have to supply certain upward force. So that upward force is equal to Fr. So typically if you have to use the ring based methods, we have to devise certain transducer based mechanisms in order to measure this Fr amount of force. If we know the Fr amount of force through certain external mechanisms, then, and if I know the weight of ring which I am using, then ultimately by using this formula I can calculate the value of sigma LF. Okay, so ultimately whatever the mechanical arrangement we are having to pull the ring in upward direction, that mechanical arrangement should be connected to some load cell or other transducers which can measure the amount of force which we are actually subjecting on this particular ring in order to move it in the upward direction. Okay, so for that we have to make some external arrangement. And the coefficient FRR is typically the function of two parameters, RR by VR power 1 by 3 and RR by RR. So these two parameters, typically how these coefficients are determined. So for determining this coefficient, we do the calibration of the experimental facility. So whatever test setup you have developed, initially this test setup you will be subjecting to some known fluid combination, for example water and air. Then you can take some common oil, glycerine and air, silicon oil and air. So all these are different types of fluids for which we already know the value of surface tension. Okay, so what we can do, we can test these different methods for different these parameters, and based on the obtained data we can actually obtain the, because if we use this type of different combinations, for this sigma LF will be already known. Okay, so in this equation we can put the corresponding value of FR which is completely satisfying this equation, and that FR data if we plot for large range of parameters and ultimately we non-dimensionalize in this functional form, then we will be getting the value of FR for different combinations of RR by R and RR by VR power 1 by 3. Here VR is nothing but the volume of the ring. So whatever ring we are using, what is its volume, that is actually our VR. Okay. Next is Wilhelmy plate method. So Wilhelmy plate method is again identical to that of the ring method. The only difference is that here instead of pulling a ring, we are considering a rectangular cross section plate, and this entire plate is actually pulled in the upward direction. So whenever you will be pulling, so initially what is done, first this plate is submerged within the interface, and after it is submerged, then actually it is pulled in the upward direction. Once we are pulling this plate in the upward direction, so Fw is the say, or Fp is the amount of force which we are applying in upward direction, Wp is the weight of the plate, and then what will be surface tension force? Surface tension force will be sigma LF into its perimeter. Okay, so perimeter of for the plate, rectangular plate, it will be, if say L is its length and T is thickness, then 2L plus 2T, that will be the perimeter. Typically the benefit of using the plate is that here, because it is not a curved geometry, so here the interface becomes actually smooth. So because of this, the contact between the interface and the plate is actually perfect, and in this scenario we need not to use any correction factor. Because of the curvature effect in the earlier methods, some correction has to be accounted for, because the wetting perimeter in the earlier cases is not exactly precisely equal to capital RR or small r. On contrary, in the plate method, wetting perimeter is actually sharply defined along the length of the plate, so that's why here correction factor can be avoided. Now second category of the methods we have called the drop shape method. So in case of force method, our aim was to first measure the amount of force, and then by using the force balance we were trying to calculate the surface tension. In case of shape method, we need not to go for estimation of force, just based on the shape of the droplet only we can actually we can characterize its surface tension. So here you can see this is the cross section of a needle. Okay, so if you take a needle and through this needle, if you allow the liquid to pump, but you have to pump the liquid at extremely small flow rates such that the inertia of the incoming liquid is actually negligible. Is this point clear? Inertia of incoming liquid has to be negligible. So this can occur in only two scenarios. One scenario can be if your size of the needle is slightly large, then you can simply pump in liquid. You can fill the needle with the liquid and then allow the liquid to fall under the effect of gravity. Other thing is, if needles are of smaller size, in that scenario there are some devices which are small flow rate pumps, typically which provides in the flow rates of milliliters per hour or even microliters per hour. So that type of pump can be connected to back side of the needle, and with the help of that pump at extremely low flow rate we can allow the drop to form. So typically you can observe, if you set your flow rates in the range of microliter per hour or milliliters per hour, you will be getting that for this much small volume of drop, say considering its spherical diameter of the order of 2 mm or 3 mm, you may take time in the range of 5 minutes to 10 minutes. Okay, so typically whenever the drop will be hanging from the needle, what will be its shape? Its shape will be pendant. Okay, so in this pendant drop, the method is having lot of derivation involved. That derivation part I am not showing over here. I am finally showing you the outcome. So ultimately what we need to do first, with the help of image analysis, we have to capture the shape of this drop just at the point where it is about to break near the needle tip and about to leave the needle. Okay, so just before that, whatever the drop shape we are getting, at this shape, with the help of image analysis, we have to fit a circle. Okay, so by covering maximum point, whatever the circle of maximum radius I can fit, which is tangent to most part of this drop, that circle actually I will be fitting. Once I have fitted this type of circle, then I can define its different dimensions. One will be R naught radius, other DE, so that is equivalent diameter. Of course it will be 2 times of R naught. And what we will be doing from the bottom side, whenever we are touching the top portion of the circle, at the top portion of the circle, how much distance it is having in which direction? This particular distance. This distance is defined as ds. Okay, now using the value of ds and de, one coefficient beta is calculated. So this relation of coefficient beta at the moment, you can consider that this is a priori known to us. However, there is certain procedure to determine this which we are not discussing over here. Okay, so you have to fit this drop shape and then you can calculate the value of this coefficient beta once you know ds by de. After calculating beta, what I can do, because ultimately why this drop shape is forming? This drop shape is forming because of the balance of again its weight and surface tension forces. So the weight will be ultimately linked to the buoyancy, balance of weight and buoyancy. Okay, so that is delta rho g r square. Okay, and surface tension force will be sigma into, so this I am talking about in order form, because ultimately surface tension force will be sigma into 2 pi. Typically it will be in the form of needle radius, but if that needle radius is scaled in terms of r naught, then of the order of, and beta is the coefficient in order to scale this. So surface tension force will be in the form of gamma into 2 pi r naught into beta. And what will be this force? Buoyancy force. Delta rho, density difference. Okay. gravity into, in order to account for the volume, what we need to do? 4 by 3 pi r naught cube. So ultimately over here, by balancing this, all the constants and other terms are accounted for in the formulation of beta, and you get that your surface tension is nothing but delta rho g r naught square by beta. Is this point clear? So this is how we can utilize this drop shape method, particularly the pendant drop shape method, for determining the surface tension. Next method is rotating cylinder method. So in case of rotating cylinder method, centrifugal effect of centrifugal acceleration is actually employed for measurement of surface tension. So here what is taken, a cylindrical vessel is taken, and inside this cylindrical vessel one surrounding fluid is considered. So surrounding fluid is typically the heavier fluid, okay, and one lighter fluid. So typically what is considered, the liquid whose surface tension we want to measure, that liquid is considered as the surrounding fluid, and small air bubble is actually injected inside the liquid, and after that this tube is rotated at very high speed. So once you will be rotating the tube at the high speed, what will be happening? Heavier fluid will stay in outside and lighter fluid will be collected at the center, and of course because of the centrifugal effect it will be acquiring some particular type of shape, okay, and that shape is having, say over here in this scenario, highest amount of thickness as RB. Now surface tension is nearly equal to omega square delta rho RB cube by 4. Okay, so using this formulation we can calculate the value of surface tension. If you have to consider the surface tension variation between two liquids, then the liquid with heavy density we will be filling with in the entire tube, and the another liquid sample which is having lighter density, that sample I will be injecting in small quantity inside this particular tube. Okay, and after that this tube is actually given the rotation. So mostly this type of arrangement is typically used for measurement of surface tension or interfacial tension for highly viscous fluid mediums. Next method is maximum bubble pressure method. Okay, so in case of maximum bubble pressure method, what is done? You have a needle. In this needle, you know that whenever drop or liquid will come out of this needle, initially how it grows. Initially its cross section, its interface will be something like this. So this is location A. When I will be further injecting the volume, then its section will be something like this, which is B. Ultimately, at certain point, it will be almost forming an hemispherical shape with radius equal to that of the radius of the needle, and after that, if I keep on further injecting the volume, then it will be sticked to the needle tip due to surface tension force. However, its remaining volume will be actually starting increasing its curvature. Okay, so in this scenario, if you see in point A, the radius of curvature was extremely large. When I have come to B, then it has decreased. At C it is minimum, and after C point it has again started increasing. Okay, so now what can happen? I can say that with time radius of curvature RC will be showing variation something like this. Okay, now what if I do, if I take my setup something like this. This is my liquid sample, okay, and in this liquid sample, needle I have placed in such a way so that it is submerged within the liquid. Now, the back end of this needle is connected to some air supply. Okay, and again this air has to enter at very low flow rate so that the inertia effect does not come into account. Okay, now at low flow rate air is entering, and at this air line we have connected some pressure transducer which will be measuring the value of the pressure. Okay, so ultimately what will be happening, whenever needle is inside the liquid, submerged inside the liquid, and we are allowing air to enter, a bubble will form at the interface. Is this one clear? So bubble will be forming over here. Now, what is the Laplace equation? Laplace equation says that if I have a bubble, then delta P is inversely proportional to radius of the bubble. It means that if I have to plot delta P as function of time, it will be initially lowest and then it will be increasing, reaching a maximum value here, and after that it will decrease. Is this point clear? So ultimately what I will be doing, because the bubble forming over here will be of different smaller sizes, and this will be depending upon the even surface tension and the needle size, etc. So what we can do, instead of recording the shape of the bubble, what we can do, we can simply record the pressure at this point. Okay, so initially whenever we will simply start injecting the air, the value of pressure will be low, and once air will start forming this type of interface, then pressure will keep on increasing, and the pressure will be having highest value when radius of the curvature is equal to radius of the needle. Is this point clear? So when radius of curvature of the bubble is equal to radius of the needle, corresponding to that it will be highest, and this will be the minimum radius of curvature. And after this point again radius of curvature will keep on increasing and the value of pressure will decrease. Is this point clear? So what I can do, I can simply use the equation that delta P will be maximum when R will be, radius of curvature will be minimum. Is this point clear? All are clear with this point? And minimum radius of curvature in this scenario is nothing but equal to radius of the needle. Okay, so by just knowing the radius of the needle and value of pressure signal, I can calculate the value of surface tension. Now here you have to simply understand that the shape is symmetric. That's why whatever the cross section is there in this plane, same cross section will be there in the transverse plane. So that's why this can be simply considered as a spherical bubble. Is this point clear? So by just observing the value of pressure, we can actually determine the value of surface tension. Is this one clear? But only thing you have to keep in mind, whenever you are allowing the air to enter, you have to allow air to enter at extremely low flow rates, because if the flow rate is finite, in that scenario what will be happening, from this point to this point there will be significant pressure drop because of the flow. So if you have significant pressure drop because of the flow, then value of delta P max, whatever you are measuring at this point, this is not going to be the value of pressure at the interface. Then at the interface, value of pressure has to be lower than the value of delta P max. Is this one clear? So this is the reason, because typically we know that whenever fluid flows from location 1 to location 2, if it flows at very small velocity, then pressure difference between these 2 points will be small. But if we keep on increasing the fluid velocity, then pressure difference between these 2 points increases. So we all know that delta P with velocity of the fluid, average velocity of the fluid varies somewhat like this way. So in laminar region it is proportional to velocity, and in turbulent region it is proportional to V power 1.75. Okay, so always whenever you will be increasing the velocity between the 2 points, pressure will be increasing. So that is what I am trying to explain you. If say this is your location 1 and this is your location 2, because at location 1 you are measuring the pressure, and whenever you are applying the formula, this formula is based on the pressure at point 2. Is this not clear? So ultimately what will be happening, if your flow rate is high, then between 1 and 2 delta P will be large. Okay, so P1 minus P2 will be large. If P1 minus P2 is large, then whatever the pressure you are measuring at point P1, you cannot tell that that particular pressure, that same pressure is there at point 2. Is this one clear? So ultimately, you can only consider P1 to be nearly equal to P2 when your velocity of flow will be small. Is this one clear? And please note it, this delta P max, whenever I am writing, it is nothing but P1 max minus P naught, where P naught is the pressure of the surrounding liquid. This point you have to keep in mind. Okay, so this is not the pressure difference between these 2 points. This is the pressure difference at location 1. Okay, what is the maximum value of pressure at location 1 minus pressure of the surrounding. Is this one clear? Okay, so with this we complete our discussion on measurement of surface tension. Now we will discuss little bit about uncertainty analysis and planning of experiments, and after that we will start our discussion on computational methods. So let us start first our discussion with uncertainty analysis. Can you tell me what is the difference between error and uncertainty? So these are the 2 terms which typically we encounter while we do the experimental measurement. One is called as error and other is called as uncertainty. Can you tell me the difference between the 2? What is error? First define error.
Difference between our absolute value and our experimental outcome.
So typically error can be defined as the difference between true or known value and the measured value. A simple example is, say, for air water system at atmospheric temperature and pressure conditions, we know that surface tension value is 0.07286 Newton per meter. If I ask you to use any of the methods we discussed over here to determine the surface tension of water and under the same conditions, and if you calculate from your experiment that your surface tension is coming out to be 0.07 Newton meter, then whatever the difference of 0.0286 Newton per meter is there, that is actually our error in the measurement. Okay. However, one important point is, whenever you have done this experiment first time, then you have got this value. But whenever the same setup you have used second time, then say you have got this value. When same setup you have used third time, then you have got some other value. So likewise, when you will be repeating the experiment multiple times, every time you will not be getting a unique value. Okay, your values will keep on varying. Now, if say fourth time you have done the experiment and you have got the value 0.015. Okay. Now you can understand that out of these 4 readings, this reading number 4 is something which is significantly different from the true value or known value, or even significantly different from the values which we measured through same experiment in other trials. Okay, so it means this particular value is having something which is seriously wrong. Okay, so some serious issue is there with this value. So I can simply say that this value is discarded. So this is something which is coming because of the known reason. We are knowing something that this may happen, that maybe I forgot to switch on the button of the transducer and simply measure the voltage, or maybe I have made a serious mistake while doing the measurement while preparing the sample or something. So whatever the value or whatever the wrong value we are getting, because of the known reason, that I will be calling the error. But here you can see the differences are coming in earlier 3 readings, and we are trying to do the experiment in the similar way. Okay, we are not changing any procedure, we are not modifying anything, but still we are having some difference in the values. So any change in the outcome due to unknown reasons is something our uncertainty. Is this point clear? So anything which is coming because of the unknown reasons in our measurement, that quantity is something which we call as our uncertainty. Now typically errors are of multiple types. So one error can be considered as gross blunder. So gross blunder is, as the name suggests, and I gave you example previously. Say you are trying to measure flow rate with the help of venturimeter, and when you are trying to measure the flow rate with the help of venturimeter, what you have done, you have 2 pressure tappings, one at this point and one somewhere over here, and in these 2 pressure tappings you have used some digital pressure transducers, PT1 and PT2. Okay, say these pressure transducers are to be connected to some data acquisition system, and you have taken the measurement, and after taking the measurement you found that this cable was not connected to the transducer. So because of that, whatever data you will be getting, of course it will be significantly, or it will be very random. So this type of mistake, which is because of the major fault while we are doing the experiment, that is called as gross blunder. Then other than that, there are some errors which are called as fixed or biased errors. What is fixed or biased error? Say I am using a transducer, okay, for measuring value of pressure, and I observed that whenever my true value of pressure is 10 kilopascal, it gives me the value of pressure as 11 kilopascal, and every time, whether I repeat this experiment 1000 times, every time it will be giving me value close to 11. So it means in the true value and the measured value there is always a finite and almost a constant gap. So once we have a constant gap, every time that error is coming, that is called as a fixed error. Typically why this error comes? This error comes because of the changes in the measurement device once it is used for long term. For example, if you use a pressure gauge, so we know that how pressure gauge functions. Bourdon tube pressure gauge, it is having some hollow tube, and from here pressure is supplied. When pressure is supplied for different pressures, the deflection of this tube happens, and this deflection is noted in terms of changes in the reading, okay, through some calibration process. So if you keep this pressure gauge for long use, so ultimately what will be happening, for after long use it will be subjected to multiple cycles of deflection and returning its shape to the original situation. So in this scenario, through its repeated use, it may happen that after some time, instead of this shape, it has already obtained some deflected shape because of the deformation of the material for its longer use. Okay, so in this scenario what will be happening, Of course, whenever you will be measuring, earlier it was here, now it is here, so it is having some initial fixed deflection present. Okay, so whenever you will be doing the measurement, every time this initial fixed deflection will be coming into your measurement. So this type of error, which is giving almost a constant difference, and which is known error, and ultimately this error is also a known error. Okay, so this we will be calling as our fixed or biased error. Okay, and the way to eliminate the fixed or biased error is either to correct the reading, because you know that this much you have to make correction, or to recalibrate the device. Then third type of error which can come is, that is called as random error. So random error which is coming because of the unknown reasons. Okay, so this can be because if one person is reading the needle of the pressure transducer, other person is reading the same needle, so there can be difference of 0.1 or 0.2. Okay, depending upon the sensitivity of the instrument and measurement. Simply there can be some unknown scenarios. For example, in one day you did the experiment and the ambient temperature was 25 degrees Celsius. Other day you are doing the experiment, ambient temperature has gone to, say, of course you have to control the experiment, but when you are controlling the conditions, then also it will not be always precise, you will not be always precisely able to control to 25.0001 degrees Celsius. It may happen that one day it was 25.5, other day it was 25.1. So likewise, these small fluctuations which will be taking place because of the any unknown reasons, this type of errors are called as random error. But one unique characteristics of the random error is there, that it will be leading to fluctuations in the reading, but these fluctuations will not be very large. And ultimately, if you take large number of measurements and you plot the large number of measurements, you will be finding that these measurements which are coming because of the random error, these will always try to follow the normal or Gaussian distribution. Okay, so measurements will try to cluster about a single mean value. Is this point clear? Because this error is because of the unknown reasons. So unknown reasons, whatever error will be coming, that will be coming in very small quantity, and ultimately in large number of measurements there is possibility that that reason can occur multiple times, though it is not known to us, but it can occur multiple times. So once the similar reason is occurring multiple times and it is because of the random fluctuations, then our data should cluster about a single value, so it should follow a mean distribution. Is this point clear? It should follow a normal distribution, but the ultimately random error is something which gives rise to uncertainty. Ultimately what is happening, because whenever reasons are not known to us, so our measurements are not certain, okay, not specific. For example, if I have recorded the data of temperature and this was like this, then I cannot say that my recorded value is 25.001 degrees Celsius. Always what I will be doing, I will be telling that, say this is my mean is 25.3, and some standard deviation if I consider plus sigma this side and minus sigma this side, then I will be telling 25.3 degrees Celsius plus minus say 0.5 degrees Celsius. So that is my uncertainty in the measurement. Is this point clear? Now, this is the uncertainty associated with the experimental measurement. So ultimately what will be happening, whenever I will be in an experimental setup, if I do 10 measurements, okay, so in each of the measurement I will be having some uncertainty associated. For example, if you simply talk about the measurement of flow rate through a venturimeter, okay, so in venturimeter, can you tell me how many measurements you have to do? You have to do measurement of this pressure, you have to do measurement of this pressure, and ultimately you have to also measure the area A1 and area A2. Okay, So there are 4 measurements. Now in these 4 measurements, if you have certain uncertainty, after that what you will be using? For estimating the velocity, you will be using some formula which is a function of P1, P2, or say for measuring flow rate, you will be using a formula which is a function of P1, P2 or A1, A2. So if in your primary parameters, these can be called as primary variables, and this will be your secondary variable which is derived from this primary measurable quantities. Okay, so if in our primary quantities we are having some uncertainties associated, then ultimately whatever the secondary quantity I am calculating by using all these primary measurements, that quantity will also be having certain amount of uncertainty. Okay, so in order to estimate the uncertainty in my resultant quantity, we have to do uncertainty analysis. Is this point clear? So for doing uncertainty analysis, let us understand it with the help of a very simple example. The example is our experiment was requiring the measurement of power, and we know that power is equal to voltage into current. So we are using a voltmeter whose measurement is in the range of 100 volts plus minus 2 volts. So there is an uncertainty of 2 volt in the voltage measurement, and current rating says that 10 amperes plus minus 0.2 ampere. So ultimately, if these are the uncertainties associated with voltage and the current measurement, then what will be the uncertainty in the power? So one of the easiest way to determine uncertainty, what I can do, I can assume that how much will be maximum deviation in voltage. So maximum deviation in voltage could be 102. So I have taken that 102, and how much is maximum deviation in current? Maximum deviation in current is 0.2. Corresponding to that, my power is 1040.4 watt. But if there was no uncertainty, then power would have been 1000 watt. Okay. Similarly, if I consider the minimum deviations in both the quantities, then my value of power comes out to be 960.4 watt. And ultimately, I can say that I have plus 4.04% deviation or uncertainty and minus 3.96% uncertainty. Okay. But one simple point is, can you consider a possibility where voltage is also giving the maximum deviation and current is also giving the maximum deviation? Is it possible simultaneously? Of course, it can happen, but the probability of occurrence of this quantity will be extremely small. Because ultimately what we are saying? We are saying that uncertainty is coming because of the random things. Okay. So whenever all the things are happening randomly and these are unaccounted, then the possibility of occurrence of an event. So of course, when we are saying the random things, it means I will be having thousands or lakhs of possibilities which can causes the fluctuations in the measurement. Okay. So out of all these possibilities, the chances of occurrence of the event where all the measurement devices are reaching the maximum deviation simultaneously is extremely low. So because of this, if I use this very simple estimate for uncertainty, it will be actually a very crude measurement, and whatever the final outcome I will be obtaining, I will be having very high uncertainty in the final outcomes. If I am having extremely high uncertainty in the final outcome, that is not considered a good design. Okay, because a good design is one which should tell that this will be our outcome with lowest amount of uncertainty. If your uncertainty in some design is actually excessively high, it means there is no need of designing that, then ultimately you go for hit and trial method. Okay, so that's why to truly measure the uncertainty, what is typically done, we consider that x1, x2, xn are our primary measured quantities, and r is our resultant, which is a function of all the primary measured quantities x1, x2, x3. Now Klein and McClintock have given an equation which tells that if W1, W2, Wn are the uncertainties in measurement of primary quantities, then uncertainty in measurement of the resultant will be del R by del x1 into W1 square plus del R by del x2 into W2 square plus so on up to del R by del x and Wn whole square and entire square root of the entire quantity. So this equation gives a good estimate of the uncertainty and it does not account for the maximum or minimum possible deviation simultaneously during the measurement. Now using this equation, if you measure the uncertainty over here, then how much value you get? 2.83. So now you can see that earlier numbers were excessively large. But if you measure the uncertainty using this method, then you are getting that 2.83%. It means there can be, whatever the final power you will be measuring, there can be deviation of plus minus 2.83% in its measurement. So here you can observe that if you consider this plus minus 2.83, then what will be your power value? 1028.3, and this will be somewhere close to 980 something. I am not measuring the exact number, but close to 980. So now you can see that whenever you are considering the earlier measurement, our spectrum of final outcome was excessively high. But now when we use the correct method, then spectrum of final outcome has actually decreased. Okay, and of course a good measurement system or a good design system will be one in which this will be as low as possible. Okay, so now let's try to see if I have the resultant quantity in the form of a power function x1, a1, x2, a2 and xn, an, then uncertainty using the previous method can be simply, so this is simple algebraic manipulation and finally you can write uncertainty in the form of this formula. Okay, so of course resultant function can have different type of mathematical forms. One of the mathematical form is considered over here in the form of product functions, and using the previous equation, this is how you can actually obtain the generalized. So this is very simple algebraic manipulation. Now this is for additive function. This is the important point, selection of a measurement method. Okay, so typically whenever we do the measurements, again for measuring power, I have now three different possibilities: current, voltage and resistance, and the individual uncertainties are also listed over here. Now if you have to measure power, you can either measure the power using E square by R or E into I. Now out of this, which formula will be most suited for estimation of power? How we can determine this? I know the individual uncertainties. I can perform uncertainty analysis using both the formulas. So if I calculate with E and R, then this will be my equation for uncertainty, and through this equation I am getting the uncertainty in measurement of power is 2.236%. If I use the second formula, which is power equal to E into I, then this is my uncertainty equation. So these are all algebraic manipulation you can do. So all the derivatives I have listed, and you will be getting measurement of uncertainty in measurement of power to be 1.414%. So it means that being a design engineer, you have been given the choice that out of these two type of measurement system, which one you will be considering for estimation of power. Obvious choice is using the formula E into I, because it is giving the least uncertainty in the final measured quantity. Is this point clear? So this type of analysis is typically done before designing the experimental setup and before selecting the instruments. So this is very useful in selecting the instruments for the experimental setup. How this is done, that I will explain you in the next lecture.